Okay, so now we're set up. So welcome Cecilie from Bath, and she will talk on challenges and interfacial problems with exponential asymptotics.
Thank you very much. Apologies for my awful PowerPoint skills, but hopefully it gets better from here. So I'd like to introduce you to some challenges that I'm working on as part of my PhD. In particular, I'm considering a class of different free surface problems, and this slide is kind of to motivate why I'm considering them as a class of problems, because they have a lot of similar properties. So firstly, the problems are going to consider incompressible, irrotational, and viscid fluids. So this is going to be potential flows. The problems are often two-dimensional, but I hope that one day we can consider three-dimensional problems as well. Importantly, we're going to have a free surface, which we're going to have to solve for as part of the problem. We're going to have a set of governing equations, and these are always going to consist of at least a Bernoulli equation, which will be the pressure balance on the free surface, and some boundary integral equation involving the Hilbert transform. And kind of key to the whole talk is that all of these problems exhibit some selection of a particular solution when we take the small surface tension limit. And in the whole talk, epsilon is going to denote the surface tension. So when epsilon goes to 0, that's a small surface tension limit. So it might be useful for me just to make a note of that to help everyone's memories. So we have a parameter that we're going to fix at each time we solve the equations. This is epsilon, and it's proportional to the surface tension. Great, so I'm going to kind of start the talk by introducing some problems that are in this class that we're kind of interested in working on at the moment. So the first problem I'm going to introduce is kind of the well-known Saffman-Taylor problem. So for anyone who doesn't know what that is, in the top picture, do I have like a light somehow? In this picture here, we have the physical setup. So we've got two parallel plates where we've got a fluid shown in gray between them. The space between the two plates is very small, so we can essentially consider this as a two-dimensional fluid, which is shown in this picture here. What we then do is inject some air from the left into the fluid, and in the steady state, we're going to end up with a single finger occupying some part of the fluid. We're always going to be looking at the steady state solutions in all of these problems. Then we've got a key parameter lambda, which tells us what proportion of the width of the fluid is occupied by this finger. And lambda is an eigenvalue of the problem that we're going to be needing to solve for. And this is okay. On the bottom, I have a set of equations. So the top equation is the Bernoulli equation. So this is a singly perturbed second-order ODE. We have two variables which are going to be consistent throughout this talk. So this is q and theta, and these are the speed and angle of the fluid on the free surface. And then we have an S, which is going to parameterize our free surface. So finally, we have a set of variables. Q, the speed of the fluid, and theta, the angle. Okay. And this is kind of the interesting part. So in this picture, which I've stolen from Chapman's paper, but there's a number of other people who have also worked on this selection mechanism, we can see that if we fix a value of epsilon, so that's fixing the surface tension, there's a countable set of lambda values which are selected. And for each of these, we have a permissible solution for the free surface. Then when I take the surface tension towards 0, all of these converge onto one single solution that's selected in this limit. And in this case, that's lambda being a half. Oh dear. Okay, so this problem has kind of been done in quite a lot of detail using exponential asymptotics, and we're able to predict this selection mechanism. But some of the next problems I'm going to show you still have open challenges remaining. So my PowerPoint issues persist, but this next problem is a slight generalization of the first one. So now, rather than parallel walls on the domain of our fluid, we've instead got a wedge of some angle. In this case, the angle is phi. And then we're again injecting fluid from the left into the region. We're injecting air from the left into the fluid region, and then the proportion of this angle to the total angle of the wedge is now our lambda eigenvalue. You can see just this slight generalization makes the equations I showed you before suddenly look a lot more complicated. So we've still got a singly perturbed second order ODE, but now we've also got a dependence on x being our physical variable. So to close the system, we're going to need more equations that I've hidden from you. But the interesting thing is that this problem shows a similar selection mechanism. So again, if we fix an epsilon, there's a countable set of lambda values that are selected, and each of these converges towards a particular solution when we take the surface tension towards 0. But in this case, the branches seem to sort of close off before we reach some particular solution. Some parts of this selection mechanism have already been derived, but to kind of predict this full picture that I've shown from the numerics on the right-hand side still remains an open problem that we are kind of trying to tackle at the moment. Okay, let me move on to problem 3 in this class, which is the Taylor rising bubble. So similarly, we've still got a two-dimensional fluid, but now the air is rising in a bubble upwards against gravity in our problem. So the introduction of this gravity means that our Bernoulli equation now has an extra term on the left-hand side, and it's suddenly even more nonlinear. And we have a Froude number which is introduced. In this problem, the Froude number is now our eigenvalue that we're solving for, and the Froude number essentially tells us the speed that the bubble is rising. So let me make a final note of this. F is a Froude number and proportional to the speed of the bubble. And here's some numerics we've done on this, showing a similar picture to before. A discrete set of Froude numbers are picked at a certain surface tension, and these converge to some particular solution, in this case with the Froude number f star 1, as we take the limit towards 0. And we've got some open challenges relating to this that we're currently working on. Some of the difficulties in this problem, people have tried to simplify this problem. One way that people have tried to simplify it is in the Jokolsky rising bubble. And the main difference here is that the far field behavior of the bubble we've just approximated with vertical walls instead. So this kind of simplifies the geometry a bit, but the payoff for simplifying the geometry is that we've introduced an extra eigenvalue b in our equation that also needs to be solved for. You'll notice that the paper I've referenced is actually from the 80s, but because the numerics now become quite difficult, even producing this picture of the selection mechanism I've been showing you before is still an open challenge. Okay, problem 5. You can imagine generalizing what I showed you on the last slide by changing the angle of those walls that we've introduced. We have a similar set of equations. We have an even bigger question as to when this selection mechanism occurs. Perhaps it depends on the angle of these walls. And the final problem I'd like to introduce before moving on is the axisymmetric rising bubble problem. So now our Bernoulli equation is going to depend on the radius and the x variable, so the depth variable, and the boundary integral equation is gone now because we've got 3 dimensions. Some people have done numerical work on this and hopefully are starting to recognize this kind of picture where we have a particular solution being selected as the surface tension goes to 0. Great, so I've talked a lot about this selection mechanism, but how do we resolve this with exponential asymptotics? And this seems a logical point in the talk to do a brief review of Saffman-Taylor for anyone who hasn't seen it recently, so I can show you the kind of idea of the method we want to apply to these other problems. So in this brief review for the next few minutes, I base a lot of my notation on Chapman's work, which is why I put his paper there. So now I've, in this top picture, taken the Saffman-Taylor geometry again, where we're injecting some air into the fluid from the left, and I've just chopped it down the symmetry axis. It turns out to be convenient for our analysis to map this to the y-plane. So we've now got the fluid in the top left quadrant and the free surface on the real axis. And finally, I have the set of equations I was showing you before, but now depending on this y variable. So the exponential asymptotic approach goes as follows. We assume some power series in our small parameter epsilon. And it turns out that Saffman-Taylor is a fairly nice problem, and we're therefore able to analytically solve the leading order. You can see in this leading order that on the bottom we have something that might sometimes be 0. We're going to get some singularities in our leading order problem, and these lie on the imaginary axis. So hopefully people are familiar with the concept, but let me explain it. So at later orders, we're going to be equating terms now at order epsilon to the 2n. In particular, we're going to have theta n minus 1 double derivatives needing to balance with theta n. So the singularity that we had in the leading order term, each time we differentiate it, the singularity is going to increase by 1. And this balance can help us to infer the form of the late order terms, where we're going to have a factorial over power ansatz to deal with this repeated differentiation of the terms. Now, a kind of key point of this analysis is that we now look at this Hilbert transform h of theta n, which is this integral on the right-hand side. And if we substitute in our factorial over power ansatz, you can show that this Hilbert transform is subdominant. So the general idea is that the functions are fairly nicely behaved. We're going to have a singularity due to this singulant function, but that's going to lie off the real axis, and we're integrating on the real axis. So that's sort of an intuition as to why we can remove this Hilbert transform. Then the second equation looks a lot nicer, and we can combine everything on this slide to derive an equation for the singulant function. Okay, now you can do a whole load of exponential asymptotics, but the kind of key idea here is that we can find the Stokes lines, which are the lines where the singulant function is real and positive, and we can plot those numerically as has been done on this left picture. So to remind you, the free surface lies on the real axis, and this is where the selection mechanism ends up being determined. So in the far field, we have some boundary conditions. So here and here, we have some boundary conditions that prevent us having any oscillations in our solution. And then when we move along the real axis, if we cross the Stokes line, we're going to be turning on or turning off some exponentially small contributions. So these are turned on or off here and turned on or off here. But because of the boundary conditions in the far field, we need to exactly turn off anything we turn on in that central region. And that gives us a solvability condition that determines those selected eigenvalues that I was showing you in the last many slides. Okay, so now we just want to do all of this, but for the other problems. But we run into a couple of difficulties, and I'd kind of like to use the rest of this talk to highlight 3 of the difficulties that we run into. So the first difficulty is that sometimes we can't solve the leading order problem analytically as we could for the Saffman-Taylor. And this means we're going to have to find this singularity structure in some other way. The second difficulty is to do with this Hilbert transform and whether we can always show that it's subdominant and cross it off in our analysis. And the third difficulty is in some of these problems that we can't do fully analytically, we need a numerical solution to sort of partner our analytical work, and we run into numerical errors when trying to produce this numerical solution. So we need to be able to deal with these issues to resolve the problems. Okay, so the first difficulty arises because sometimes we can't solve the leading order problem analytically. We still need the singularities for the exponential asymptotics, so we need to find their structure numerically. So let me give you an example of some work we've done for the rising bubble case. So this is the leading order equations, which we can't solve analytically, mainly because of this kind of term that gets introduced. We've written these equations in terms of the potential plane. So now the bubble, the nose of the bubble here is at the origin, and the free surface lies on the positive phi axis. And we're able to numerically solve these leading order equations. And here you see one such solution where the angle is pi by 2 at the nose of the bubble, and then it converges towards pi in the far field. Okay, so we've solved it on the positive phi axis, and now we're going to analytically continue these equations into the complex f-plane. So we use some initial condition from this numerical solution, and then we solve the equations along some path into the complex plane. So the path is shown by the dashed line, and then the solid line is showing us the values in the complex plane. When we do this, I just note that theta now becomes complex. So in this picture, we just plotted the real part of that complex theta. Okay, so ideally we'd follow a lot of paths into a complex plane, and we can explore the complex plane, and we can look for the singularities and the branch points that we couldn't find analytically. So we've done that for this problem. Here I've shown the path that we've taken. We started on the free surface. We've moved anti-clockwise around the origin. And I just wanted to note that because the origin is a branch point, by the time we get round to here, we're actually a Riemann sheet higher than the fluid. So we're not intersecting the fluid, hence the dashed line. And here's some of our results. So this is one of the singularities that we found. We found a number of singularities. When the Froude number is small, so our bubble is rising quite slowly, the singularity lies here in this complex plane. And then for increasing values of the Froude number, the singularity moves around and spirals in and appears to spiral right into the origin and coalesce with it at some critical Froude value. So yeah, this is slightly peculiar behavior. It appears that at the critical Froude number, all of the singularities, this being one of them, coalesce with origin, and then for larger Froude numbers after that point, they're all gone. So this is still some work in progress to understand this picture fully. Nice. So let me move on to the second difficulty, which was to do with the Hilbert transform. And I think it's useful here just to go back to the Saffman-Taylor for a moment. So in the Saffman-Taylor, we had a nice analytical form for the leading order problem. And what I'd like to highlight is that here, because of this y on the top, we've got a stagnation point at the origin. But the stagnation point behavior is linear, so when we differentiate our leading order problem, we're not going to get any issues due to that. We're then able to write a factorial over power ansatz with the singularities that were on the bottom here, and we're able to argue away this Hilbert transform. So here are two other problems which look very similar. Firstly, they have stagnation points at the nose of the bubble, but we weren't able to solve these analytically, so we don't actually know whether these stagnation points are linear or whether they're some branch point-like behavior. Secondly, this problem, here the fluid is going around an angle greater than pi, so we've got some singular behavior here. So we have all the singularities we might find in the complex plane, and then we've also got potential singularities in our late terms arising due to the stagnation points and these singularities. So essentially, I think we should write our late order terms as a sum of factorial over power ansatzes for all of the singularities, because we're not sure which one is the dominant important one. So this then means that when we're doing our analysis, we get to the Hilbert transform, and we're going to end up with a Hilbert transform for each of these factorial over powers. So ideally, we want to show that each of these is subdominant, so we can cross them all off, and then we can continue merrily on our way with the analysis that we normally do with no Hilbert transforms involved. But I think it's quite difficult to show that all of these are subdominant, and potentially it's not even possible for us to do that in some problems. And therefore, I've kind of reached a few questions that I'd like to pose to the audience. Firstly, can the singularities or the branch points on the free surface ever end up dominating the behavior? We've kind of struggled even to come up with a toy problem where it would dominate the behavior. So if anyone has any experience or something like that, I'd be interested in talking to you afterwards. Secondly, assuming it could dominate the behavior, what would that mean for the Stokes lines? Normally we have a Stokes line emanating from some singularity in the complex plane, and we're integrating back to the free surface. But now we're already on the free surface. So yeah, what does that mean? Thirdly, there appears to be some work by Kessler and Levine which deals with sort of singularities and branch points that lie on the free surface. In their work, they take like an inner region close to the key point and then an outer region away from that in their analysis. But they don't have any Hilbert transforms. So to be able to use that, we'd at least need to build on their work to incorporate some sort of boundary integral into it. And a final thought we had whilst we were throwing the kitchen sink at this problem is to use some numerical work to gain insight. So let's say we could produce a reduced model where we just naively crossed out the Hilbert transform. We could then solve that problem numerically and compare the results to the numerical results for the full problem. You might be able to see if they're very similar, that the Hilbert transform wasn't so important. So I'll leave this as a kind of question and then move on to the final difficulty that we encountered. So this is to do with numerical errors from the typical way of solving these types of problems. So here I've taken the rising bubble problem, I've chopped it in half down the symmetry axis, and then we're going to map it to the t-plane just because that's more convenient for the numerical method. So now the free surface lies on the outside of that half unit circle. Then the numerical method, the key point is that we write our complex velocity as an analytic series. And we're going to truncate that at some high value of n. The effect that this has is we're able to essentially remove this equation. So this equation was ensuring that q and theta are holomorphic functions. And here we're implicitly assuming that q and theta are analytic functions. So we end up just needing to solve Bernoulli's equation with this assumption for the complex velocity. So the method goes as follows. We divide our free surface into a number of mesh points. And then at each of the mesh points, we solve Bernoulli's equation with this substituted in. And we're solving n+1 equations with n+1 unknowns. We can use Newton's method. And the n+1 unknowns are the n coefficients, and mu being the angle at the stagnation point. Okay, so we try to do this, and the numerical method doesn't work amazingly, so an improvement of this method is to include this prefactor term, which accounts for some of the behavior. In particular, we want this prefactor term to account for the behavior at the stagnation point. So it ends up looking like this, which basically locally is the behavior of a fluid moving past a wedge of angle mu. Okay, so now we have a numerical method, we solve the equations, and we run into some numerical issues. So these are some of the symptoms of the numerical issues I've tried to highlight here. In this left plot, we have the coefficients, and you see that they have this horrible sawtooth pattern in them. Ideally, we'd want them to kind of decay smoothly as n increased. In this picture, we have the free surface profile, and very close to the stagnation point, we have, again, a sawtooth pattern at each of our mesh points that we chose. And finally, the value of mu is not the right value of mu. This should be a π/2. So it turns out that the numerical method here is under-predicting the value of mu. This is a key problem which is causing these other two issues. And I think the reason is that, the reason is that if we over-predicted the value of mu here, we'd have some singular behavior that the analytic series would need to account for. So the numerical method prefers to slightly under-predict the value of mu. So we came up with a hack to solve this problem, where we switched out the mu, so we're now going to fix mu instead and solve for f, the Froude number. So in this left picture, I don't know how well you can see the purple line, but the coefficients now become nice and smooth. In the central picture, again, there's a purple line showing that the free surface now becomes smooth even at the stagnation point. And finally, because we fixed mu, it's exactly the correct value of π/2. So this is great, but I've already got a problem where this hack doesn't work. So this is the Jokolsky rising bubble problem. We've got a stagnation point again, but we've also got some singular behavior here that we'd like to encode in our g of t function. The issue is that the singular behavior here depends on other eigenvalues in our equation, and we're not sure how it depends on the other eigenvalues. So we can't fix both the behavior here and the behavior here without knowing how they relate to each other. So this means that we've still got some work to do to come up with a new hack that can deal with problems like this. So that's everything. Thank you for listening. I'd be interested to hear any questions or comments.
Any questions?
Yeah, just a few remarks. The stagnation point problem, the semicircle is the right approach because you don't have, you have removed the singularity. That with the problem you're facing at the edges, you have to resolve those singularities.
Yeah.
But still, any even weaker singularity causes the decay rate not to be sufficient because you only resolve up to a certain order. Mm-hmm. So instead, what you could do is use the problem with the power series is that any problem on the boundary shows up in the coefficients.
Yeah.
So instead, you could decide, instead of uniformly spaced out points on the boundary, you could space your points closer to the singular point and solve for a real f and use the Hilbert transform relation between real f and imaginary f on the boundary.
Okay. Yeah.
So that would actually make it easier to solve the problem. In the hunt for complex singularities that you did, you could actually go outside and analytically continue. So I can talk more about it later.
Thank you. Yeah, I'd be interested to talk more.
Thanks. I was wondering, the singularity that you had in theta, was it a function on the complex potential plane and you're walking around?
Sorry, I can't quite hear you.
You had like a singularity in theta. You plotted a real part of theta and then a path. Yeah, a few slides ago.
Yeah. This one.
Yeah, that one. So do you know what type of singularity that is? Is some branch point or?
Yeah, so I
Just
think
a
this is a square root branch point.
Okay. And do you see that in the, is there a T-plane version of that? Like, do you see it outside of the semicircle you drew?
Yeah,
the
I guess it would
T-plane.
map to somewhere outside of the semicircle
you don't know
in
where.
the T-plane.
Because have you thought about maybe doing like a Pade approximant in the T-plane to see if you can see where that guy is or something like that? I don't know, just an idea.
Yeah, I've not considered that.
Okay.
So be
We'll talk about it
interested to,
later.
yeah, let me know your thoughts later.
So I noticed you've got the 3D rising
Yeah.
shape. And I was just sort of thinking, obviously it has radial symmetry, which means you'll be able to get this nice cancellation. Have you thought whether it is possible for this sort of behavior to arise in sort of non-reducible 3D geometries? I've thought about that a bit and can't quite work it out.
Yeah, so I've not thought particularly about that yet. My approach is to attempt the axisymmetric case before we move on to that.
That's
but
very sensible.
Yeah.
I was just sort of curious if you had speculated.
no, I've not thought a lot about that yet.
I just had a couple of comments. On this singularity at the nose, so I think one of the reasons I went to y instead of s was to square that s to the half so that it became a y, and then it disappears.
Yeah,
Because I think that singularity is a red herring, and therefore
I see.
I got rid of it by changing coordinates. So I'd be
So
surprised
perhaps
if it
there is something
contributes.
similar you can do in the other problems.
Yeah. And the other comment was to do with this, that often when you take the limit epsilon goes to 0, the number that it appears to is where the singularities coalesce, because that's the place where the Stokes lines from the individual singularities will be very close to each other, so that you've only got one
Yeah,
wavelength between them, for example. So
yeah,
even just seeing where they coalesce without doing anything else will probably tell you what the critical fruit number that you're going to approach is.
yeah. Thank you.
Okay, any more questions? Oh, another one.
In the problem where you have this difficulty one, you show the numerical
Sorry, I can't quite hear you.
expression. You can hear me now?
Oh, that's better, yeah.
It's better, okay. This difficulty here, you once showed a numerical solution which had seemed to asymptote to a certain value.
Yeah,
Yes.
this one.
Does it asymptote exponentially towards a finite value?
Yeah, I guess this is
Yeah,
asymptoting towards pi as we move towards pi here.
does
So
it
you
do
could
it
do some-
exponentially?
I don't remember off the top of my head, but you can definitely get the far-field behavior.
Because if you have an exponential behavior, this can tell you something about the singularity. At least the imaginary part of it.
Yeah.
Mm-hmm. Oh, okay.
Old. I think this is like Garabedian's work.
Yeah.
This would be like free streamline flow at the bottom. So it's just like jet analysis. And you can write, I'm not sure what plane it is.
Are we talking about we're talking about fluids, right?
Fluid rising against gravity.
Correct. So in this case, conservation of fluid, because it's going under gravity, it will accelerate. So that means that the side, it must approach the sidewall as it accelerates because the mass flux is bigger.
Yeah.
Yeah.
So it approaches the sidewalls in a very
Big algebraic.
Okay, I think then we'll postpone other questions for tea, which is now, and we are back at 3:50 for the last talk of the day. Thank you. Thank you very much, Cecilie.
Thank you.